Hi, everyone. So today, Roan's going to give us a talk about the structure and statistics of tree space. If you're watching this on YouTube, please like and subscribe. And I'll pass on to Roan now.
Thank you. I'm Roan Talbot, for those of you who don't know me. I guess a little bit of information about kind of where I'm coming from with this. I'm in my fourth year now, and I've kind of predominantly done more pure courses throughout my time at Cambridge, so kind of some geometry and probability stuff. But more so this year, I've become really interested in some of the statistical ways that aspects of pure maths can kind of relate to other areas of the world, I suppose. A lot of the stuff in this talk is going to come from a slightly statistical kind of motivation, but a lot of the content is going to be more based in geometry. That being said, a lot of these ideas are not things that I've come across from any courses in particular, so I've tried to kind of keep the prerequisites to a minimum. I will kind of also, as a result, not be getting into the technical details too much. My aim here is to kind of try and show you guys how a lot of these different mathematical ideas can kind of relate to one another, and convince you guys that it's some really fun stuff to look at in more detail. And yeah, like I said, I've kind of tried to break it down into different sections, so if you have any questions about the technicalities of one bit, I'll kind of have a break where you guys can check up before I move on to the next bit. Cool, so what do I mean by tree space? The thing we're trying to understand here is tree data. So this is basically data where each individual data point is a tree. So this is like a graph or a network with no cycles. And this can arise in a lot of different situations. So on this slide here, I've got the arteries in the brain as one example. And this is one example where actually we can identify the exact tree through kind of imaging processing or whatever. I'm not an expert on that. But we can identify the exact lengths of each of the edges in our tree and exactly where all of the splits are happening. But then another example is phylogenetic trees. So here we've got phylogenetic trees for different species, different languages. These trees are, again, kind of in and of themselves a type of data, but they're actually constructed from other data which we're kind of more familiar with. So a lot of these trees will be constructed using some kind of similarity metric between kind of DNA or words in the different cases. So in terms of kind of why this is something worth studying, from a kind of non-mathematical perspective, it is really valuable because, you know, particularly in the phylogenetic tree case, it gives us some sense of how species and languages can evolve. And in particular, that could be really useful for predicting mutations of viruses, for example. But on the other hand, it's also really mathematically interesting because it's incredibly hard to construct, or it's not immediately obvious in any way how to construct a metric on trees, which is kind of an inherent first step if we're trying to do any kind of statistics here. We want some idea of when trees are similar, and for most statistics we would want to just kind of put it in Euclidean space, but in doing this with trees we often end up with trees which to most of us would look very similar, but for some reason the metric is saying that they're quite far apart, or kind of vice versa. So we end up with serious issues with kind of embeddings into Euclidean space. So what I'm talking about today is some of the different spaces we could use instead. And so I'm going to be looking in particular at two different spaces, and then I'm also going to go into some detail on how we can then develop statistics in these different spaces, with the particular example of some sense of principal component analysis in BHV space. So these two spaces, the first one, BHV space, is what I'm probably going to spend a bit more time on. It builds on some things that I was looking at last summer, and there's been a lot more done on this approach. So we have some sense of principal component analysis in this space. There's also been work developing a type of Hamiltonian Monte Carlo methodology with this, which is particularly useful if we're trying to do any kind of Bayesian statistics. But then a slightly newer approach relies on tropical geometry, and I'm not as I don't have as good an understanding on the kind of technical details of this approach, but for several reasons, it's kind of potentially a more promising approach. So I want to kind of try and highlight some of those reasons for you as well today. Okay, so getting into the maths of it. The first thing that we need to do is we need to be clear on exactly what set of trees we're considering, because this can vary quite a lot depending on the exact application that you're considering. So we're going to be talking today about phylogenetic trees, so these kind of evolutionary trees that I was showing you earlier. And so from these, we're insisting that they have a fixed number of leaves at the bottom, which are the species or the languages that we're considering. They've evolved from one shared root, which we've got at the top of our tree. And sometimes we'll represent this by a vertex with degree 2, but other times we can represent this by sticking a 0 leaf on there as well. And those two are pretty much equivalent. Of course, it doesn't matter the kind of symmetry of the tree in sense of like we can swap 1 and 2, and that makes no difference in a kind of evolutionary perspective. That's meaningless. So we don't want our kind of space to be sensitive to those kind of symmetries. And then finally, we also are only particularly interested in the lengths of our interior edges. So we are considering trees with kind of specific edge lengths, but we're not going to worry so much about the exterior edges. And this is kind of mostly because the length of the exterior edge lengths might be dependent on things like exactly when we're kind of observing this. So like if we're considering this as like some sense of the time that's passed between one evolution to the next, the exterior edge lengths are kind of less significant because that's just like the amount of time that's passing at the moment. So we're only going to keep track of the interior edges, and we don't worry about the exterior edge lengths. Which means we get our first definition of the trees that we're considering. We're considering rooted trees with capital N labeled leaves, and they are equivalent up to external edge lengths. So the first thing to note is that trees are uniquely defined up to their topology and the internal edge lengths. The topology being the kind of splitting pattern of the vertices. So if we then just focus on one specific splitting pattern or topology, then we're only caring about internal edge lengths, and it's then quite easy for us to then use Euclidean space, and we just give that a kind of Euclidean geometry, where basically our coordinates are determined by the lengths of each internal edge length. So here we have an example. We have we're looking at trees with 4 labeled leaves, 1, 2, 3, 4, and the 0 is our root. And this will have at most 2 internal edges, which gives us this kind of quadrant here. When we're talking about kind of higher dimensions, I'm going to be referring to those as orthants. It's just a higher dimensional quadrant. And on each side of this quadrant, we have lines which are effectively equivalent to like degenerate trees, where we have kind of splits, more than one split happening in one go. So we have 1, 2, and 3 all splitting at the same place. Or we have kind of 3 and 4 splitting at the same time as 1 and 2 coming off as well. And basically this idea of kind of the degenerate topologies allows us to join these orthants together. So we're going to use the standard Euclidean metric within a single orthant. And then we will join together two orthants along their kind of borders according to when they kind of share a degenerate topology. And then the metric on the entire space can just be defined as the shortest path between 2 points. So here we have kind of one central line, which corresponds to the case where 1, 2, and 3 all split from the same vertex. And then coming off from this line, we have 3 different orthants, which correspond to the 3 different ways we can resolve this kind of degenerate topology. So hopefully at this point you're comfortable that I've kind of roughly defined our space and given it a metric. You're gonna have to just trust me that it is a metric. But this doesn't actually give us very much information as to the structure of this space, which is particularly important if we want to be able to make any develop any kind of statistical methodology or draw any conclusions from it. So if we want to try describing the structure of the overall space, what we're going to be using is simplicial complexes, which is something I came across in 3rd year algebraic topology, so don't worry if that is not something that's familiar to you. It can effectively just be thought of as like a higher dimensional version of a graph, where we have vertices, we have edges, but then we also have kind of 3-point collections or 4-point collections, which are these triangles and the tetrahedron. And these are all kind of 0 to 3D simplices. And I think one thing in particular to note about this is that whenever we have a kind of k-dimensional simplex in our simplicial complex, we also have all of the lower dimensional simplices that border on it. But if that's confusing to you, the summary is that it's like a higher dimensional version of a graph, in the abstract sense where we don't have edge lengths or anything. So using this concept of simplicial complexes in order to describe our space, we do this by considering the structure at our origin. Because all of these orthants have the same origin. It's all the star tree, which is basically when we have from the root everything splitting at the same place. So if all of our orthants meet at this one point, then we actually can deduce that understanding the structure at this one point tells us the structure of the entire space. And another way to think about this is actually just that the whole space is actually a cone. We can scale the internal edge lengths, either kind of like arbitrarily big or kind of shrink them all to 0, and then we reach our kind of star tree. So describing the structure at this vertex is done using the concept of a link. And a link is a simplicial complex where we basically replace every a k-dimensional orthant with a k-1 dimensional simplex. And then we join up the different simplices using the same gluing rules as we used for the orthants. Another way of defining it that is equivalent is just thinking of it as like taking the like epsilon sphere around our vertex. And just to kind of give you a concrete example of how this works, on the left here we have the same diagram from earlier where we have 4 kind of half lines coming out from our star tree, which is the one at the bottom here. And each of these 4 half lines is going to correspond to one vertex in our link. We then join up those vertices according to when we have a plane joining up those 2 half lines. So the two-dimensional planes correspond to edges, the half lines correspond to vertices, and these kind of join up. And if you kind of think about this as well, hopefully it's also clear where the kind of concept of like an epsilon sphere comes in as well. If we just consider the structure of points at a distance epsilon away from our star tree, we get a space that looks a bit like this. But this is obviously just one localized point, again, of our space, and we want to be able to understand the entire space. And in this case here, where we're talking about trees on 4 leaves, this gives us actually the Peterson graph, which is quite fun. This is the Peterson graph, for those of you who are not familiar. Basically, it's kind of 3 regular graph. Well, I think we just have 5 cycles. It's a nice graph that appears in lots of different places. So just to reiterate again, basically each of these edges corresponds to a quadrant, a 2D quadrant, and they are joined together at these vertices. We also on this diagram have the exact topologies of each of these orthants shown. And like I was saying, the simplicial complex is like a higher dimensional version of a graph. In the case of kind of 4-leaf trees, we end up with a graph because we only have 2 internal edges. And because we only have 2 internal edges, we're only going to end up with at most 1-dimensional simplices in our simplicial complex, which gives us a graph. Okay, so that's kind of a lot. I just want to double check right now if anybody wants to ask any questions, and just check about their understanding of that before I start talking about well, means and principal component analysis.
I have a question. How quickly, like when you go to more than 4 initial leaves, how quickly do you build up much more complex simplices in these? Like, is it at 5 it suddenly becomes really complex, or like, yeah?
That's a good question. I think the number of I think the dimension increases at the same rate, so it's like it's just linear. I think the kind of complexity of the resulting link or simplicial complex can, like, the size of it grows much larger. I can't remember the exact relation, but the dimensionality doesn't necessarily blow up, but the kind of size of it in terms of the number of vertices and the number of each simplex we have grows quite quickly, I think. Okay, that's a good question. If there's nothing else, I'll move on to the next bit. Okay, so in terms of now trying to do statistics in this space, which sounds a little bit bizarre, but actually we do have some really useful results right off the bat. In this space, geodesics and Frechet means are unique. So basically this means kind of geodesics are just the shortest path between any 2 points, and Frechet means are the kind of point which minimizes the sum of squared distances to points in our data set. So, you know, in standard Euclidean space, that is just the normal concept of a mean, but it can become more complicated, and we don't necessarily have unique means in other spaces, but luckily we do here. And in terms of the results which give us these kind of unique Frechet means and geodesics, it follows from these 2 lovely results here, which I'm not going to get into in too much detail, but for the kind of geometrically curious amongst you, it's really nice results. effectively, the idea is to show that this space has some sense of global non-positive curvature. It suffices to show that it's just kind of locally non-positively curved because of this, because of the fact that it's a cone. We can just shrink everything down to our star tree, and we only need to consider the structure at that point. And then showing that it's locally non-positively curved can basically just be done by considering the link at the vertex and showing that this link is a flag. When I say flag, this basically means that for any k points in our simplex, we have the simplex, sorry, if we have k vertices in our simplex, and we have the simplex on any k minus one of them, then we must have the simplex on all k of them. And if that condition is true, then we have a flag. And this kind of combinatorial condition is enough to show that we have non-positive curvature, which is quite nice. So if that is of interest to you, it's quite cool that that just pops up. But that's basically how we can show that these things are unique. Given that they are, what kind of stats can we do? So we're going to try and reconstruct the concept of principal component analysis, which is basically just about trying to capture what our data looks like using fewer dimensions. And so there are kind of two ingredients that we need to consider. What it means to have a lower dimensional subspace of our tree space, and then some sense of projection to take our data points, which aren't necessarily in that subspace, into the subspace whilst kind of losing as little information as possible. So if we're looking at subspaces, in standard Euclidean geometry, subspaces are very easy to describe. We can just describe them by kind of k points and using them as a basis. But we don't have a linear structure on our tree space. So instead of taking a kind of the kind of linear space generated by our basis, we're instead going to think about just taking the convex hull of these k points. So we can't necessarily kind of extrapolate, but this kind of gives us some sense of kind of interpolating. Unfortunately, we can't just take the convex hull. One of the difficult things about this space that makes it harder to work with is that for a fixed number of just 3 points in our space, we can have an arbitrarily high dimensional convex hull, which is unhelpful. So what we're going to do instead is we're basically going to just do the first step of taking the convex hull, which is this process of taking weighted Frechet means. And luckily these means are unique. So what we've got is kind of a well-defined map that goes from the k-dimensional simplex. Here I'm talking about like the possible weights on kind of k different points, which kind of sum to 1. And then given kind of k plus 1 points in our tree space, this map goes from our simplex into our tree space. So this is one way of defining a k-dimensional subspace of our tree space, given k plus 1 points. So the next thing we need to do is talk about some sense of projection. And effectively, we have an algorithm to do this. It's effectively just looking for the point in this subspace which has minimal distance to our data point z, And this algorithm that we're using is effectively just starting at a point, kind of starting at one of the corners of our simplex, and then just walking in a fixed direction towards a different corner in the direction that minimizes our distance to z. It's not perfect, in particular because this space isn't convex. If it was, it's a convex hull, but we've already mentioned that it's not the convex hull. There's not necessarily a unique projection, but we can kind of approach a local minimum for this kind of projection distance, and it kind of converges to a similar point each time. So we're going to kind of work with it and see how the data ends up looking. Given this concept of a subspace and projection, we then it then just kind of results in needing to find the subspace that minimizes the kind of information lost by projecting. So minimizing the sum of distances from our data points to their projection. And then given this, we can kind of write down an R statistic which kind of summarizes how well our data fits to the subspace we're looking at. And we're going to have a quick look at how this really looks for some actual data. And so the data that we're going to be looking at is the evolution of 8 different Apicomplexian species. I think this set of species, I think one of them is responsible for malaria, so it's, you know, important stuff. And actually we can generate lots of different trees which we kind of consider representative of the evolution taking place, by considering the different genes that they share, and how these genes differ from species to species. So for a fixed gene, we can construct a tree, and then for each of our genes, this gives us a set of trees to consider. We then go about doing our principal component analysis, and this funky picture is what we end up with. So this is kind of 2-dimensional principal component analysis, and we've mapped this triangle into our tree space. And there's a lot of things to talk about here. Firstly, one thing to note is that this triangle is going through lots of different orthents in our tree space, which is why we've got all of these different colors here. So these different colors correspond to the different orthents that our triangle is passing through. And on the right, you can see these different topologies that correspond to the different orthents. In particular, one thing that's really interesting is this second topology, which is kind of orange, and it's this kind of thin wedge a bit above A. The interesting thing about this is that it's corresponding to a degenerate topology. And so the orthent that we're passing through there has a lower dimension than all of the other ones, apart from topology 7, but we've got the same problem there. And what this effectively is showing us is that when we move the weights on our different data points, or kind of equivalently wiggle our data points around a little bit, our freshly mean is actually ending up stuck. It's stuck in this low dimensional space. Basically, even if we're moving our weights or our data points, our mean doesn't move. And this issue, which is sometimes kind of referred to as sticky means, is a significant issue, because you know we want our kind of, we want to be able to understand exactly when our data is kind of wiggling a bit. I think the last thing to talk about here is this kind of R statistic value that we end up getting, 56%. Doesn't sound like very much, but I think the key thing to remember here is just how impressive this is in the first place. We have trees which have like 8 leaves, and so kind of in order to capture that much information, we would normally need high numbers of dimensions, but we've managed to kind of summarize them, like summarize at least half of the information there in just 2 dimensions. And I think that's the kind of really exciting thing about what's going on here. Kind of using a more natural kind of geometry for our underlying space, we can kind of capture the information in a more natural way. Okay, that's my next pause point. So I'm not sure if you guys have any questions about that so far before I start talking about tropical geometry.
Oh, thanks, Roan. I'm not sure I followed that much, but so just to clarify, we do this kind of, when we say PCA, we're like trying to find a lower dimensional subspace which kind of gives a good fit to the data.
Yeah.
I think that's what we're kind of doing here, and that triangle is like the simplex which we're mapping from.
Yeah.
But does that, to start with, we need k plus 1 points? Is that the construction, or k points or whatever? And how do we go about choosing the best points to get the best subspace?
Right.
Yeah.
So
that actually makes sense.
yeah, I think so. So basically, the k points that we're choosing are the corners of the triangle. It's basically how we can best pick these corners in order to pick the best subspace. And I think it's fair to ask about, because it's kind of the step that I skipped over in this little explanation of how we're going about this. I think from what I can remember of the paper, it's effectively like a kind of greedy algorithm. You can just kind of keep moving one of the corners and seeing if moving it a bit improves the kind of information lost. I think it's a lot more of a kind of like proof of concept than really proving that it works perfectly or anything. But we can theoretically do this and end up with something that looks cool.
Okay, great, thank you. That made a lot of sense.
The next interpretation of tree space that I want to talk about is built from something called tropical geometry. And I'm going to kind of try and motivate this, but I'm not necessarily going to get into the details of how we can start developing statistical methodology in this context, but I'll highlight at the end some of the ways that it's kind of could be viewed as kind of better than the BHV interpretation. So the first question is, what is tropical geometry? And effectively, this is going to sound very strange right now, but the idea is that we're doing algebraic geometry, but using the tropical algebra, which is kind of, as I've written here, instead of taking standard addition, we take the maximum of 2 elements, and instead of taking multiplication, we take addition. And this may sound very bizarre, but it's actually got a lot of different applications in kind of a lot of different fields. I think a lot of this stems from the fact that it's quite good at dealing with kind of combinatorial conditions, which is already something we've had to think about in this kind of tree context. And it kind of comes up again here as well. So in particular, what are we interested in about about tropical geometry? Well, one way that tree data is kind of often constructed is by considering a metric on its leaves. This is kind of how a lot of phylogenetic trees are constructed. We just consider how similar different species or languages are to one another. So if we start considering trees as the metric on its leaves, then we can kind of describe trees using more algebraic expressions. So firstly, it's a metric. So we've got the all too familiar triangle inequality that we need to deal with. But we have tropical geometry to hand, so we can just tropicalize it, which gives us this very neat expression. And just to kind of explain a bit about what's going on here, we're having to take these kind of minus signs of our metric. Sorry, I forgot to mention, by considering the metric on endpoints, we can also view this as just a kind of symmetric matrix with positive entries. So we're doing a kind of matrix multiplication here. And we're having to take the minus signs of our matrices because we want to take the minimum, whereas standard addition is taking the maximum. So this kind of matrix multiplication is basically taking the, for each j, we're adding together kind of wij and wjk, and that's our kind of multiplying. And then we just take the minimum or maximum of the negative over all j, and this will give us back the kind of direct distance between I and k. It's not something you need to understand in a lot of depth, but it's definitely something you can kind of show easily yourself. So yeah, we can also consider these kind of symmetric matrices as just a vector in kind of capital N choose 2 dimensions, and we'll just denote these with a subscript sometimes. So again, we're just going to kind of refresh exactly what we're talking about when we talk about trees. In this context, we're now not going to worry about having a root, and we do this again by just sticking a 0 leaf on our root. So we can just consider the set of unrooted trees with kind of n labels on its leaves, and we are still going to not worry as much about the external edge lengths, but this time we only worry about them up to kind of shared additive constant. So it doesn't matter if we just extend each of the external edges by 1, we consider that to be kind of the same tree. And algebraically, this is equivalent to multiplying tropically our metrics by a constant, because multiplying is just adding, and we're just adding a constant to the each distance. So we've talked a bit about kind of representing metrics using tropical geometry, but we need to be very specific about when metrics actually represent trees and not just arbitrary metrics, because not every metric is going to represent a tree. And in particular, the condition that we need is this 4-point condition that I've got up here. Effectively, what this is saying is kind of between any 4 points, any 4 leaves of our tree, if we consider taking kind of 2 pairs and summing the distances between the 2 pairs, and there are 3 different ways to do this, then the 4-point condition says that we will achieve that maximum twice. And these are basically, like the diagram I've got at the bottom here, is the 2 different tree topologies we can have on 4 leaves. So in terms of showing that this condition kind of holds for tree metrics, you can basically just look at the possible tree topologies and convince yourself that it holds in these situations. And it's a bit more involved, showing that it's kind of a sufficient condition, but again, that's like not something I'm going to get into too much today. So again, we're kind of writing this in tropical geometry, and actually using tropical geometry in a much kind of deeper way. We can understand the structure of this entire space. You know, we're using algebraic expressions to define which kind of W vectors work, which is kind of a lot of the work behind like algebraic geometry. You know, understanding the structure of a space given kind of algebraic expressions that define it. And so, how can we actually define, or how do we describe this set of tree metrics? And for those of you who are kind of very keen on algebraic geometry, these are the nice deep results that we've got behind what's going on here. Basically, the 4-point condition that we were just looking at is the tropical version of the Plucker relations, which are used in kind of standard algebraic geometry to describe the tropical Grassmannian, or sorry, the normal Grassmannian. So the way we can kind of tropicalize this expression, firstly, we kind of, when we tropicalize an expression, minus signs just become addition. Our multiplication is becoming addition, and our addition is becoming taking the maximum. And then on top of that, instead of considering the roots of an expression, in tropical geometry, we're often interested instead in the hypersurface, which is defined to be the points where our space is kind of non-linear or not smooth. Because all of our expressions are set up using either maximum or addition, any function is going to be piecewise linear. And so the interesting thing about kind of trying to understand these functions is considering the boundaries of our kind of linear pieces. And so this is what we mean by the hypersurface. It's the place where these linear pieces are joined up, and at those points we're having our maximum achieved twice, which is what the 4-point condition was talking about. So this is kind of how we can kind of tropicalize these Plucker relations, and then using those we can construct and start to talk about the tropical equivalent of the standard Grassmannian. And this space actually, it's a subspace of the kind of projective space, and in our context we're talking about the tropical projective space. So basically, this is where we're really explaining the fact that matrices are equivalent kind of up to some scalar constant. finally, actually kind of describing the metric that we've got on this space. We inherit our tropical metric from the tropical projective space, which is given here. And so we're talking about a subspace of the kind of tropical projective space, which in a lot of cases can make things more difficult statistically, because we don't necessarily know kind of which points in the kind of underlying space are allowed and which aren't. But the nice thing about this is we do have a clear condition which describes kind of the actual tree space that we're considering. And although we don't have unique geodesics or means anymore, we do actually still have a kind of linear behavior, which is incredibly useful. So in particular, kind of the key ways of kind of comparing the tropical approach to BHV space. Primarily, we do have this kind of inequality between the two distances that we've constructed, and this is basically a way of saying that if we agree that kind of trees are close in BHV space, then they are necessarily close in the tropical space. The next thing is that the tropical metric is defined by distances between leaves, and this is, I think, a particularly important idea, because a lot of our kind of trees that we will be working with have often been constructed by distances between their leaves, and so this approach will potentially kind of make it much easier to consider this kind of statistical approach, not necessarily as like a two-step process, but a kind of bridged two-step process, I suppose. Like we can relate the construction of the trees to the kind of statistical interpretation of the trees. The next thing is that we can kind of construct some sense of geodesics in tropical space using the kind of linear structure of the space. And this is much easier to do because we can kind of write down an expression for it in using like linear terms. So kind of computationally, this is much easier. And this is a big benefit because, you know, the whole point to exploring these different interpretations of tree statistics is avoiding the kind of skyrocketing dimension of that we would need in a Euclidean space. And finally, we have had like some attempts at kind of tropical geometry interpretation of principal component analysis, and these approaches have actually often captured more of the variance of our data sets than the BHV interpretation. So from this perspective, it's immediately kind of much more promising as a way of describing large data sets. Okay, that is all I have. Here are a lot of the kind of key books and papers that a lot of this information has come from. That is all I have. Yeah, let me know if you have any questions.
So where are we in terms of going from theory to practice? Like, is this actively used in evolutionary science, or is it just at the cusp of it?
So I think so far a lot of this stuff is kind of predominantly used by mathematicians or kind of bioinformatics people, more so than kind of pure biologists. I think there have been kind of a lot of these papers do kind of try and actually do a kind of proof of concept using kind of real data sets, And I think there have been some kind of interesting observations that have come from those, but I'm not sure that I'm not very clued up on the biology of it all, so I haven't looked into those as much.
Well, thank you very much. I mean, it was a very, very interesting talk. So I think.
Maybe I should know this. So can I construct the tree from the distances between the points? This is presumably true and kind of easy to see.
I haven't thought about the most efficient way of doing it, but I think there's kind of
The standard.
yeah. I think there's also like a large set of programs and strategies for constructing trees based on metrics. People just keep referencing different R packages. I'm not sure what they
Thanks.
I guess if no one else has any other questions, thank you so much for giving this talk. It was very interesting.